Okay, so now we're going to conclude our series of videos on numbering systems by exploring the octal numbering system and then conversions from octal to other numbering or to other bases. Okay, so as you can see from this table, octal is base 8. We've already explored base 10, base 2, and base 16. And we've already explored conversions between these numbering systems. So now, knowing that we're going to be dealing with octal, which is a base 8 numbering system, how do we count? How will it progress? So let's start with a rough count in octal. So we know that we're going to need 8 counts before we add another digits. So typically we're going to start with 0, then it will be a 1, then it will be a 2. Now remember, all of these are going to be base 8. Then it will be a 3, then it would be a 4, 5, 6, 7. So now I have 8 counts, which means now I have to increase the number of digits required to continue counting, and the next one will be 10. That means you're going to have to reset the least significant digit, add a new digit, and then work from there. So what's the next thing? That would be a 1 1 up to 1 6 1 7, and guess what's going to happen right there? You will get 2 0. Right? So that is the progression. So again, you'll get 2 1, and then you continue on, then you'll have 2, let's say 7, the last one. Okay? So what's going to happen now? Well, you're going to get 3 0. So again, you're going to add 1 to the most significant bit, reset the least significant bit back to 0. So this will continue on, right? So let's say you've reached 7 7. So what do you think is going to happen? Okay, so remember, any of these digits can only reach 7, its max value. Okay, so what's going to happen here, just like when in decimal numbering system, when we reach 99, which is the max value for each digit, we go to 100. Well, guess what? We're going to go to 100 and then start over. So 1 0 1, 1 0 2, and then you continue on to 1 0 7, and guess what's going to happen? 1 1 0. Again, this pattern right here repeats itself. So we're going to repeat this until we reach 1 7 7. Right? So there's a whole series of numbers here. And then what's going to happen now? Now you get to 200. Okay? All right, so I hope you got the idea and the progression for octal numbers, how they, how to count. So knowing that, so let's focus on this part. So that means we have 8 combinations. Right? So first combination 0, 1, 2, 3, etc. until we reach 7. That's 8 combinations. So if we had to convert this to binary, how many bits or binary bits would we need to represent 8 combinations? Right? So 2 to the n equal 8. We want to know how many bits, n being the number of bits, to represent this in binary. Well, 2 to the third is going to be equal to 8. Now you could do log if you want, but you need at least 3 bits to represent any of these octal numbers from 0 to 7. So what's going to happen beyond that? Well, you're going to need an extra bit. So to represent anything higher, you're going to need 4th bit, 5th bit, 6th bit, and so on. So you're going to have to adapt the size of your binary number for larger values than anything from 0 to 7. Okay, so let's start with our decimal values. So we have 0, 1, 2, 3, 4, 5, 6, 7. I'll continue on. 8, 9, 10, 11, 12, 13, 14, and 15. I'm going to do the same thing we did in the previous videos, where we stopped at 15, and then you can continue on if you want to have fun. So for this, we know the binary value for any of these. So remember how we did this. Go ahead and put 8 zeros right here. So 1, 2, 3, 4, 5, 6, 7, 8 for the most significant bit combination. 1. You know for this you need 4 bits, right? So if you want to count to 15, you're going to need 4 bits. So I'm making sure that we have, so this is a good review or what we have done before. Let me just draw horizontal lines so everything is lined up. We don't get confused as to which value belongs to what. And in other words, what we're doing here is a conversion within a table. So it's all nice and neatly put here for us. Okay. Now I urge you to do this as an exercise. Okay. Hands-on. There's nothing better than hands-on to really get the gist of what is it you're looking at, how does it work, what's the relationship between these bases. Okay, and then you'll be much, you'll be very comfortable doing conversions as well. Now this one I'm going to put 4 zeros. So notice the technique here, right? So it's really 8 zeros, 4 zeros, 2 zeros, and 1 zero, the alternation. So the opposite will be ones. So here, 4 ones, 4 zeros, and you finish it up with 4 ones. The next one is 2 zeros, 2 ones, 2 zeros. This is one sure way not to make a mistake in terms of the progression in counting in binary. Makes life a lot easier. Okay, and then alternate starting at 0, 0, 1, and this is the least significant bit. 0, 1, 0, 1, 0, 1, 0, 1. So I hope this is a good review of what we've done before. And there you have it. So these decimal values have an equivalent binary. We know also they have an equivalent hex. Okay, so that would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now in hex we haven't reached, which is base 16, so we want to keep 1 digit until our 16th count, and then beyond that we add another digit. So in that case you can't put 1 0 here. This is why we substitute 10 with an A. B, so that way we are using a single digit to represent a number. A, B, below the size of the base. A, B, C, D, E, and F. Beyond that, you will get 1 0. All right, well, let's see how it is in octal. Again, 0, we've seen this, so what's going to happen is all of these numbers are going to be transposed here. 2, 3, 4, 5, 6, 7. We've reached, right, the max we could do here. Now watch this. To represent anything from 0 to 7, remember I told you only need 3 bits. And is that true? Yeah, notice the most significant bit here is 0, so that doesn't change. So it has no effect, so it's a padding. So if you add a 0 to any number, it still is that number, right? Whatever that was. So the 0 is just a padding. So as you can see, in this chunk right here, from here to here, the most significant bit is a 0. So really what changes are these 3 bits, right? 3 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1 1 being the last one. So what's going to happen now? Aha! Then what's going to happen is you're going to need 1 0. There you have it. Okay? Just like you would have needed 1 0 for 16 in decimal. And in binary, you're going to need an extra digit and reset the others. Right? So this would be the binary value beyond 15, which is for 16. Notice now I need 5 bits to represent 16. So it's beyond the scope of the table that goes from 0 to 15. So you're going to have to expand the number of bits you're going to need. This 1 0 here is in hex. This 1 0 here is in octal. Okay? So this 1 0 is not this 1 0. Neither is this 1 0 equal to this 1 0. Okay? So, but notice that 1 0 happens when? When you go beyond the base. Okay, what is that? At 9, after 9, you get 1 0. After F, you get 1 0 for hex. And after 7, you get 1 0. So that's a nice little pattern to know. So it doesn't matter what base you're going to have. If you have base 20, base whatever, you're going to know that 1 0 will follow along right after you're done with the base count. So what's going to happen here? 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, 1 7. And guess what's going to happen here? 2 0. Very good. So if you guessed it correctly, you're doing good, because right after that, here's your 2 0 right here. Okay? So that's the progression count for octal. Okay, so now how do we deal with conversions? Right? So we could use this table to convert right away. So 10 decimal is really 12 octal. Okay, but how did we get there? How did we go from 12 octal being 10 decimal? Now remember what I showed you before, how to go from, let's say, base 10 to base 2. Right? So what you did is you divided by 2 all the way. Can we divide by 8? Right? Or can we do something like that? Or in the other way is, can we do, remember when we did binary 2 decimal, right? So let's do an octal 2 decimal. Now remember when we did binary 2 decimal, we went by the weights. Well, let's see if we could do that. Let's take our 1 2, which is octal, and see if we can convert it to decimal. So we know this one right here is weight. The weight is what? For this one. Right? So the weight for this one, right? It's the base, right? To the power of the position. So it's 8 to power 0. Right? The weight of this one. And then the weight of this one is 8 to the power 1. Now, what is the content? Where you're going to have 1 times 8 to the power 1 plus 2 times 8 to the power 0. Can we see what that is? Sure. 1 times 8 is what you get here, plus 2 times 1, what you get here. So what is that? That's 8 plus 2 equals 10 in decimal. So that tells you that 12 octal is 10 in decimal. And is that true? Sure. So if we look at 12 octal right here, it's 10 in decimal. Fantastic. Can we go the other way around? And can we go from 10 decimal, so can we do decimal to octal? yeah, we're going to do a division just like we did with binary. Remember, I mentioned that before. So let's say I have 10 decimal and I want to go to octal. Okay, so I'm going to divide by 8. Okay, and I'm going to say how many 8s are in 10? I know there is 1. And what's the remainder? 2. And then you're going to say to yourself, can I divide some more? No, you stop here because the value you have is below the base. So this will become your most significant digit, and this will become your least significant digit, and you're going to read it this way. So what is that? 1, 2, and sure enough, and this is octal, that is 12. So 10 decimal again is 12 in octal. Okay? So let's look at 10 decimal in binary. Right? So that's 1010. Agreed? Okay? So now let's convert now this to binary. Now each one of these digits is going to be just like we did with hex, but we did it with 4 bits. This time, be careful, you're going to do it with 3 bits. So what is 2 represented in 3 bits? So that's 0, 1, 0. And what is 1 represented in 3 bits? 0, 0, 1. So what does that lead? Well, that would lead to this. This one are just padding zeros. So that takes me to 1, 0, 1, 0. Notice how easy the conversion is. Aha! So the conversion from octal to binary is fairly straightforward. You use each octal digit is represented by 3 bits in binary. Okay, let's do another example. So let's say I have 14 in octal, and I want to represent it in binary. So again, 4 represented by 3 bits is 1, 0, 0. And 1 represented by 3 bits, again, is 0, 0, 1. So we can get rid of these 2 zeros since they're simply padding leading zeros. And I'm left with this. Now let's go to our table and look at 14 octal. Remember, this is 14 octal. What is the equivalent right here? So as you can see, it's 1, 1, 0, 0. Okay, so I hope that helps you understand how that works. So let's say now you have a binary number, 1, 1, 0, 1, 1, 1, 0, 1, 1, 0, and you want to convert it to octal. Well, fairly straightforward. You do the reverse process. You pick 3 bits at a time, right here, 3 bits at a time. Now this one you can pad it with 3 zeros, right here, and then convert each one to its equivalent decimal value. Okay? When I say decimal value, it's really octal value since you're going from 0 to 7 for any of these combinations. So 1, 1, 0, you look at the table, right? So 1, 1, 0 is 6. So this is 6. Another 6 here. And then 1, 0, 1 is a 5, and that's 1. Okay? And this is base 8. So it's 1,566 in octal for this number here. So again, octal could be used as a shorthand to represent large binary numbers. But we know hex is even better because you can take 4 bits at a time, right? So you can represent even larger numbers, right, with a single digit. So this is why you would see hex a lot more than octal. One of the reasons, okay? So don't be surprised if you see systems that work with the octal counting system. Okay, so there are some computing systems that still use that. Hex is much more prevalent. But that's overall how these conversions are done, how these numbers are represented, how do you count either in decimal, binary, hex, and octal. Okay, so I hope these were very instructive for you, so what I urge you to do at this stage is to go through a whole bunch of exercises to make sure that you solidify your knowledge and you have full confidence in understanding how they work and how to convert them. On that, I will see you again for the next lessons. Thank you.